We're back talking about the pinhole camera, and this week we're going to be discussing angle of view and angle of coverage. Hey fellow photographers, what did you shoot today? We're going back to the blackboard to do some more math regarding pinhole cameras. So let's start with the pinhole camera, something like this with a small hole. And we have light rays that come into this camera kind of like this. Now, one property of pinhole cameras is they don't really have a focal length. A focal length would imply focusing of some sort, and we have no lens here, so the light rays aren't being focused in any sense. They're just being sort of projected from one area straight across in a rectilinear fashion to our film plane or image sensor. But what does happen is, depending on where we put this film plane, we do get an angle of view that corresponds to an equivalent focal length. So imagine if we put a film plane or image plane or sensor very close to the pinhole. Let's say right about here. Well, this distance is very small. And as you can see, the rays that this film plane can capture are very wide. So it can actually capture almost the full gamut of rays that are coming in from this very, very wide angle. And we haven't talked about lenses yet, but a short focal length results in a wide angle picture. And you can kind of see why in this sense. But what happens if we move the image plane outward? Now, we're not going to draw a big image plane here because that would be changing the image plane size or the film size or the sensor size. But let's just imagine that we keep the image plane the same. Let's say this is a sheet of 4x5 film, and we just move that back. Now look at these rays that come out in this direction. See, we're not capturing any of the light that comes from rays that are wider than this image plane. What's actually happening is we have a narrowed angle of view. So it's almost as if the new angle of view is something like this. Notice how we can only capture these narrow bands of light, because if they go out here, they're not going to be caught by the sensor or the film or what have you. But we're only capturing this narrow band, and that's why this longer focal length gives you a more telephoto effect. It's almost like we're zooming in on our image. So if our image is somewhere out here, the wide angle will capture images and light in this range, the entire range in fact, but a longer focal length, a more telephoto, a more zoomed in focal length is only going to be able to capture this middle portion here. So just an important distinction that pinhole cameras don't necessarily have focal lengths. This is sort of the distance of projection, but because of the light rays that the different distances can capture, it gives us the perceived notion of focal length. And in most of my videos, I use this term focal length interchangeably with projection distance, and the math works out to be the same. So if you hear me say focal length, this is the distance from the pinhole to the image plane is what I'm referring to. So that brings us to our next topic. It'd be really nice to be able to capture a super wide angle of view, but how wide can this get? And we're going to find that how wide these rays can get is dependent on two things: the thickness of the material that we make our pinhole out of and the diameter of the pinhole. So let's talk about angle of coverage. So what I'm going to draw here is a gross exaggeration of a pinhole. So let's say that this is our pinhole, and we're looking at a cross section, so this is the thickness of our material. Now, based on the thickness of the material and the diameter of the pinhole, it's going to determine our angle of coverage of light rays coming in, because essentially only the light rays that are going to clear the thickness of the pinhole are going to be able to make it through. Now, again, this is not to scale, and this is a gross exaggeration because we're dealing with very, very thin distances, but the math will still work the same. So let's call this total angle of view, which will end up being the angle of coverage, the maximum angle of coverage. Let's call this 2 theta, where theta is just an angle. So that's what this is here. This angle will be the same on both sides, and you're going to see why this is a 2 theta in a second. So if we look at this midpoint, and we drop a line down, and we make a right triangle here, so we make this right triangle. If this whole angle is 2 theta, that means that this half of the angle is just theta. So we're dealing with the angle theta, which is this angle right here. Now let's introduce some variables. So we'll call the diameter of the pinhole, the entire diameter, we'll call that d, right? So this distance would be 1/2 of d, this distance here. And we'll call the entire thickness of the material we're working with t, so that this distance here will be 1/2 of t. Now we have everything we need to solve for this angle, because we can use trigonometry to find that the tangent of theta, this angle here, so tan of theta is going to be equal to the opposite over the adjacent side. So the opposite side is going to be 1/2 of d, which is the diameter of our pinhole, and the adjacent side is going to be 1/2 of t, which is like this. So we can simplify this a little bit because the half and the half will cancel out. So tan of theta is equal to d over t. So let's put some numbers in here, and we can solve for our angle. So this pinhole camera that I referenced before has a material thickness of 0.005 inches and a pinhole diameter, so this is t, and d is equal to 0.3 millimeters. So now here's the issue, right? We have to have both of these in the same units. So we're going to stick with millimeters because that's what most cameras are accustomed to. So I'm just going to erase this for a second. And if we convert this to millimeters, basically what we would do is we could go to Google and say convert inches to millimeters, and it would do it for us. Or we can use dimensional analysis, and we would just take 0.005 times, this is inches, 1 inch is 2.54 centimeters, and 1 centimeter is 10 millimeters, right? So instead of doing that, we can just plug it in. So this ends up becoming 0.127 millimeters. So now we have both our units in millimeters, and we're just going to come down here, and in order to get to theta, we have to use the inverse tangent function. So we're going to take the inverse tan of d over t, which in this case is 0.3 over t, which is 0.127, is equal to theta. So our angle theta is going to be equal to about 67 degrees, which means that this entire angle, 2 theta, is going to be 134 degrees. So that is the angle of coverage that this size pinhole with this thickness material and this diameter is going to give us. Well, what does that really mean in realistic terms? Well, when we know the angle here, we can find out where we can put our film plane or our sensor so that we don't get the image circle will be able to fully cover that sensor. We might, when we go really wide and we put this very close, we're going to get vignetting effects, which we'll talk about, but we'll still get full coverage. So let's take a look at what that looks like. So what is an image circle? Well, I'm going to do my best to draw sort of a 3-dimensional representation here. This is our film plane. Let's say this is a piece of 4x5 film like the one that goes into this camera. We basically have an image circle that's going to project onto this plane. Now, how big of an image circle that is going to depend on the focal length or the projection distance from the pinhole. So let's just say that the pinhole is somewhere way out here, right? And we're always concerned about the diagonal of the film plane or the image sensor, because if we took just the horizontal or the vertical or the horizontal component, we might not get full coverage. You can imagine that if you had a circle that was only based on this here, it would not give you coverage to the corners. So we're always looking at the diagonal because we want the entire film from corner to corner to be covered. So we can kind of draw this out here. So imagine this triangle, which I will highlight. So from here to the corner and on the diagonal, this is the triangle that we're interested in. It's a right triangle with that angle as the right angle. And again, this angle here is theta. This is the same theta from before, which we had as 67 degrees in our example. Now we're curious to see basically at what focal length, we'll call this F, F will be this side here. At what focal length will we still get full coverage of this film plane? Now this is going to depend on film size. So if this is a 4x5 negative, again these are inches, so we have 4 inches by 5 inches. We can do some conversions to make those into millimeters and then use Pythagoras' theorem, a squared plus b squared equals c squared to find the diagonal, because remember this is a right triangle here. It's a 4x5 triangle, and then we can calculate this. The diagonal for a 4x5 piece of film turns out to be 162 millimeters. So half of that distance is going to be 81 millimeters. So this we know is 81 millimeters. So now we have, again, everything we need to find this missing value. We know what theta is, we know what half of the diagonal is, so we can solve for the focal length. How do we do that? Well, we're going to use the tan function again. We could also use similar triangles if you're not comfortable with trigonometry. But what we're going to do is we're going to say that tan of the same angle theta is equal to the opposite over the adjacent side. So we have 81 millimeters over f, and we're going to solve this for f. We can flip-flop these two, so we know that f is equal to 81 millimeters over tan of theta. From before, we actually know that tan of theta is equal to d over t, so we could plug d over t into here, solve for f, and it turns out that f, in this case, is going to be equal to 34, I wrote this down, 0.29 millimeters. So this is the minimum focal length where we will still get full coverage of the image plane for this particular pinhole of a given pinhole diameter and a pinhole thickness. So on a 4x5 negative, that is actually extremely wide. You might not think 34 millimeters is wide because you're probably thinking in terms of full frame cameras or crop cameras, but on a 4x5 negative, that is insanely wide. That's probably somewhere close to 9 millimeter equivalent on a full frame. And if you know anything about that kind of wide angle glass, this would be rectilinear, so it's not even a fisheye. That would be some very expensive glass to manufacture. So you can go really wide. Now there is a problem with going this wide. Yes, we have full coverage of the film, but it's just barely full coverage. So the image circle, the projection, the sort of area of coverage is going to be something like this. It's going to be just enough to cover the image plane. And that's going to introduce some heavy vignetting. Vignetting is when the corners of the picture are darker than the center. And we haven't talked about the inverse square law of light yet. That's coming up, don't worry. But essentially, think about it this way. The light has to travel a shorter distance to the middle. This distance is shorter than this distance here. So because light has to travel a further distance here, it's less bright when it gets to this point in the corner than when it gets to the center. So let's take a look at what this looks like. So let's go back to the beginning where we had our pinhole like this, and let's put our film plane here, right? And this will represent some sort of wide angle of view. Now imagine the distance from the pinhole to the film plane is something like that. And if we were to make a circle with that as the radius, it's close enough. These are all the points that are equidistant, the same radius from the film plane. Now notice how the gap, so this is light traveling into the pinhole from all directions like this. Now notice how, even though these distances are the same, the distance to the middle of the film versus the distance that light would have to travel, it would have to travel this extra amount to each of the corners. This gap is pretty large in comparison to the distance here, the radius of this circle that I've drawn. So we're going to get heavy vignetting in the corners because the corner is very far away from sort of this line of equal illumination, if you will. Now, imagine what's going to happen if we take this same film size and we push it out a little further away from the pinhole, and we have a new projection length or focal length. And then we draw a circle that has a radius of that focal length. Something kind of like that. Now notice how in proportion notice how this gap between the corner of the film plane and this light of this sort of arc of equal illumination is much smaller. It's smaller both in absolute magnitude, but more importantly, it's smaller in proportion to the light, to this long distance here. So it's a small fraction, whereas this is a big chunk of this piece. This is only a small piece of this piece. So in a further focal length, we're going to get more even distribution of light on the film plane or the sensor, so we're going to get less vignetting, less effects due to vignetting. So you can go extremely wide, but you risk vignetting. If you go further back, you're not going to get that wide angle of view that we talked about, but you're going to have less darkness in the corners. Now, what's the other extreme? The other extreme is if we put the film plane something, I'll erase this quickly. So ignore that for a second. Actually, we can just erase this whole thing. So the other thing is, what if we put this film plane, it's about the same size, very close, but our maximum angle of coverage is only something like this. Well, if we take a look at our photograph, we're basically going to have a circular picture that's going to be equal to the image circle. We're going to get something like this. These corners would be, these border would be completely black. So we calculated the minimum focal length needed to get full coverage. It will be with heavy vignetting. Anything further away from that is going to give you a narrower angle of view, kind of a zoom effect, a telephoto effect, and it's going to give you less difference between the corners and the center of the image. You're going to get less vignetting on those kinds of pinhole cameras. So this is all just things to be aware of. One last thing is, on this pinhole camera that I made, if you notice, there's a large circle here before it even gets to the sort of thin pinhole material. And that's because this has great thickness in relation to the material, the brass that's in here. And that's because the light actually has to pass through this thick wood before it even reaches the pinhole. So you want to make sure that this hole is wide enough based on the thickness of the other materials you use so that you still get the maximum amount of light coming through the pinhole. And once you calculate the maximum angle, that 2 theta, and in this example it was that 134 degrees, try and build your camera to that specifications to let the maximum amount of light in, and then you can worry about how far you want the focal length to be based on the angle of view that you want. But you want to give your pinhole every fighting chance of capturing as much light as possible. So don't build something out here like this that restricts the light coming into the pinhole, because then you're just going to narrow your angle of view even more. So I hope that was an informative look at what causes the image circle and the coverage and the focal length of pinhole cameras. And next time we're going to talk about tips and techniques how to compose images and what makes good subject matter for pinholes. And until then, happy shooting.